Pick a number, any number. Go ahead, think of one right now. I am willing to bet it does not start with 1. And the reason I know that is because you are a human being, and human beings are terrible at generating random numbers. You probably picked something starting with 7 or 3 or maybe 5. That is what people do. They spread their choices around. They aim for the middle of the number line because the middle feels random. It feels fair. It feels like what randomness should look like. Nature disagrees. If you take the lengths of every river on Earth and write them down, roughly 30% of those numbers start with the digit 1. If you take the populations of every city in the world, 30% start with 1. If you take stock prices, street addresses, earthquake depths, electricity bills, the masses of stars, the drainage areas of watersheds, the half-lives of radioactive isotopes, the rotation frequencies of pulsars, the molecular weights listed in any chemistry reference, the numbers printed in this morning's newspaper, roughly 30% of all of them start with the digit 1, not 10%, which is what you would expect if digits were distributed evenly. 30%. Meanwhile, the digit 9 shows up as a leading digit less than 5% of the time. And this is not a rough tendency. It is not an approximation. It is a precise mathematical law with a formula you can write in a single line. And it has been confirmed across hundreds of datasets, spanning river basins and tax returns and genome sizes and pulsar catalogs and the Fibonacci sequence. It has been used to catch tax cheats, convict embezzlers, flag fabricated scientific data, and investigate stolen elections. It has been admitted as evidence in court. It has been applied to the economic data of entire nations, and nobody can explain why it works. That is not an exaggeration. That is not me being dramatic for effect. In 2011, the two mathematicians who had spent more time on this problem than anyone alive published a paper in the Mathematical Intelligencer with the title Benford's Law Strikes Back. No simple explanation in sight for mathematical gem. They were not being modest. They were being precise. There is no back-of-the-envelope argument, not even a heuristic one, that explains why the digit 1 dominates the numbers that nature produces. The mathematics can tell you that the law must hold if certain conditions are met. But the question of why those conditions are met so often in the physical world, why the universe builds its numbers this way, has no accepted answer. It had no accepted answer in 1881, when it was first discovered. It has no accepted answer now. What nobody knew in 1881 was that the man who discovered this pattern had just written down a formula that would eventually be used to convict criminals, audit governments, and expose the largest accounting frauds in modern history. He published it in 2 pages. It received 1 citation in 57 years. And the law does not even bear his name. His name was Simon Newcomb. And to understand how a self-taught Canadian astronomer stumbled onto one of the strangest patterns in all of mathematics, you need to picture what a working scientist's desk looked like in the late 19th century. There were no calculators. There were no computers. If you needed to multiply 2 large numbers together, or compute a square root, or do anything involving exponents, you reached for a book of logarithm tables. These were thick, heavy volumes filled with columns of pre-computed values, and you used them constantly. You flipped through them the way a modern programmer flips through documentation dozens of times a day. Every astronomer, every physicist, Every engineer who worked with numbers kept a copy on their desk, and they wore those books out. The spines cracked, the pages loosened, the binding gave way in predictable places because the pages that got used the most suffered the most damage. Newcomb noticed something about his copy. The first pages were falling apart. The pages near the front of the book, the ones containing the logarithms of numbers starting with 1 and 2, were stained, dog-eared, and visibly more worn than the pages near the back. The pages for numbers starting with 8 and 9 looked almost new, and this struck him as strange, because if you are computing with random numbers drawn from the real world, you would expect to need every part of the table roughly equally. But the wear pattern said otherwise. The wear pattern said that in practice, the numbers scientists actually work with start with low digits far more often than high ones. Not slightly more often, dramatically more often. The front of the book was being destroyed while the back was barely touched. Now, you might think this was a quirk of Newcomb's particular field. Astronomers work with distances and luminosities that happen to start with certain digits. Maybe the pattern was specific to astronomy, but Newcomb did not think so. He thought it was universal. And in 1881, he sat down and worked out the mathematics. He published a 2-page paper in the American Journal of Mathematics, Volume 4, Number 1, pages 39 through 40. This was a journal he himself edited, which tells you something about the institutional dynamics at play. The opening sentence is worth hearing exactly as he wrote it. That the 10 digits do not occur with equal frequency must be evident to anyone making much use of logarithmic tables and noticing how much faster the first pages wear out than the last ones. In those 2 pages, he derived the complete formula, the probability that the first significant digit of a naturally occurring number is d equals the logarithm base 10 of 1 plus 1 over d. He even worked out the second digit distribution, which runs from about 12% for 0 down to about 8.5% for 9. He published a numerical table identical to what would later be called Benford's law. And at the bottom of the paper, almost as an afterthought, he wrote a sentence that I think is one of the most quietly brilliant observations in the history of mathematics. It is curious to remark that this law would enable us to decide whether a large collection of independent numerical results were composed of natural numbers or logarithms. Stop and think about what he was saying. In 1881, 112 years before anyone actually did it, Simon Newcomb was describing forensic accounting. He was saying that you could use this pattern to tell the difference between real data and fake data. He saw the forensic implication before there was a forensic science to apply it to, and he buried it in the last paragraph of a 2-page paper that nobody read. Nobody cared. The paper received exactly 1 citation between 1881 and 1938 from the experimental psychologist E.G. Boring in 1920. 1 citation in 57 years. The most important pattern in numerical data sat in plain sight for more than half a century, and the entire scientific world walked past it. Not because it was wrong, not because anyone tested it and found it lacking, because nobody noticed. The paper existed. It was correct. It was ignored. I need to stop here for a moment and tell you about the man himself, because the biography matters. It always matters. The circumstances of a person's life are never separate from the discoveries they make. Simon Newcomb was born on March 12, 1835, in Wallace, Nova Scotia. His father was an itinerant country school teacher who moved the family frequently. His mother, Emily Prince, died when Simon was still young. The family was poor, and education was catch as catch can. At 16, his father apprenticed him to a man named Dr. Fauché, an herbalist and supposed healer in New Brunswick, who turned out to be a fraud and an abuser. The apprenticeship was essentially indentured servitude. Newcomb was bound to Fauché for 5 years and expected to work without meaningful compensation. He endured it for a while, but Fauché was a charlatan who practiced quack medicine, and the arrangement became intolerable. So Newcomb ran. He literally fled through the woods of New Brunswick while Fauché hunted for him. He walked south, crossed the border into the United States, and kept walking. He had no money, no connections, and no formal credentials. What he had was a mind that could not stop working on mathematical problems and a desperate need to find a place where that mind would be valued. He eventually talked his way into the Nautical Almanac office in Cambridge, Massachusetts in January 1857. He later called it an epoch, an entrance into a new world. He was 21 years old and essentially self-taught. Within a year, he was enrolled at Harvard, where he studied under the mathematician Benjamin Peirce and graduated summa cum laude in 1858 with a Bachelor of Science. He then proceeded to become the most respected astronomer in America. He served as director of the Nautical Almanac office for 20 years. He collaborated with a young Navy officer named Albert Michelson on measuring the speed of light, producing a value of 299,860 kilometers per second in 1882. He became the first president of the American Astronomical Society in 1899 and served until 1905. He won the Royal Astronomical Society's gold medal in 1874. He was promoted to the rank of Rear Admiral upon retirement in 1906. President Taft attended his funeral in 1909. He titled a chapter of his autobiography, The World of Cold and Darkness. His only son died in infancy. His daughter, Anita Newcomb McGee, went on to found the United States Army Nurse Corps. This was not a fringe figure. This was one of the most accomplished scientists in the Western Hemisphere, a man whose contributions to celestial mechanics are still referenced in orbital calculations today. And his 2-page paper on digit frequencies, the paper that contained the formula, and even the forensic insight, vanished without a trace. The man who ran from an abusive apprenticeship, who crossed a border on foot with nothing, who taught himself mathematics from borrowed books, discovered one of the most universal patterns in all of data science, and the world shrugged. That should make you angry, because what happened next makes it worse. 57 years later, in a General Electric research laboratory in Schenectady, New York, a physicist named Frank Benford noticed the same worn pages. This is where the story should have been corrected. Benford should have found Newcomb's paper, cited it, and moved on. He did not. There is no evidence that Benford was aware of Newcomb's work. He appears to have made the observation independently, staring at the same kind of logarithm tables, noticing the same pattern of wear. 2 men, half a century apart, looking at the same artifact and seeing the same thing. But Benford did something Newcomb never did. When Newcomb wrote 2 pages and moved on, Benford became obsessed. Frank Albert Benford Jr. was born in 1883 in Johnstown, Pennsylvania. I want you to remember that city name because it matters. When Benford was 6 years old, on May 31st, 1889, the South Fork Dam failed upstream of Johnstown. A wall of water traveling at roughly 40 miles per hour hit the town. It killed 2,209 people in a matter of hours, making it one of the deadliest disasters in American history. Entire neighborhoods were erased. Bodies were found as far as Cincinnati. Benford was a child. He survived. The historical record does not tell us where he was when the water came or how his family endured it. But the fact is that he grew up in a town that had been destroyed, rebuilt, and haunted by the memory of catastrophic failure. Whether that shaped his later temperament, his dogged insistence on testing and retesting, on gathering data until the pattern was undeniable, is the kind of connection biography invites but cannot prove. What it can prove is that the man who would give his name to one of mathematics' most enduring laws began his life in a place that had been remade by random catastrophe. Benford grew up, took an electrical engineering degree from the University of Michigan in 1910, joined General Electric the same year, and spent his entire career there. He worked first in the Illuminating Engineering Laboratory for 18 years, then in the Research Laboratory for 20 more. He was a practical physicist, an experimentalist, and an inventor. He designed the ellipsoidal reflector spotlight in 1923, the ancestor of the modern theatrical Leco lamp. If you have ever been in a theater, you have sat under lighting that descends in a direct line from Frank Benford's optics work. He published 109 papers and held 20 optical patents. He was not a mathematician. He was an engineer who noticed a pattern in logarithm tables and refused to let it go until he had tested it on everything he could find. And when I say everything, I mean everything. Benford spent years collecting data. He did not test the pattern on one dataset, or 2 or 5. He tested it on 20. He gathered 20,229 individual observations. Let me walk through what he actually tested, because the specificity matters. It is the specificity that separates Benford's paper from Newcomb's. Newcomb had the formula. Benford had the evidence. He tested river drainage areas from a geological reference. He tested the populations of United States cities. He tested physical constants from a handbook. He tested molecular weights. He tested atomic weights. He tested specific heats. He pulled numbers from an issue of Reader's Digest. He looked up the first 342 street addresses listed in the reference book American Men of Science. He recorded American League Baseball statistics from the 1936 season, 1,458 individual data points. He tested X-ray voltages. He tested pressures. He tested the brightness of stars. And he tested several tables of pure mathematical values, including square roots, reciprocals, and factorials. Across all 20 datasets, his weighted average for the leading digit 1 came out to 30.6%. The theoretical prediction from Newcomb's formula was 30.1. The agreement was astonishing. And it was not just the digit 1. Every digit, 1 through 9, fell almost exactly where the formula predicted. Digit 2 appeared 17.6% of the time, matching the prediction of 17.6. Digit 3 appeared 12.5%, matching 12.5. The entire distribution, not just one data point, but all 9, followed the logarithmic curve Newcomb had derived from pure mathematics 57 years earlier. Except Benford did not know Newcomb had derived it. As far as Benford knew, he had discovered something new. He read the paper to the American Philosophical Society on April 22nd, 1937. He was introduced by his colleague Irving Langmuir, who had won the Nobel Prize in Chemistry the previous year. The paper was published in 1938 in the Proceedings of the American Philosophical Society, Volume 78, Number 4, pages 551 through 572, 22 pages. Compared to Newcomb's 2, it was a monograph. 2 sentences from that paper deserve to be quoted exactly because they reveal something about how Benford thought about what he had found. These are not technical statements, they are philosophical ones, and they point at the mystery that remains unsolved. On page 554, he wrote that the logarithmic law for large numbers evidently goes deeper among the roots of primal causes than our number system unaided can explain. And on the final page, 572, he closed with this: the theory of anomalous numbers is really the theory of phenomena and events, and the numbers but play the poor part of lifeless symbols for living things. Remember that phrase, primal causes. I am telling you about it now, not because it is interesting background, but because it connects directly to where this story ends. Benford sensed something in 1938 that the mathematics still cannot articulate today. He felt that this law was not about numbers at all. It was about the processes that generate numbers. It was about the way the world works at a level deeper than arithmetic can reach. And nearly 90 years later, the finest mathematicians alive have confirmed his intuition. The law does go deeper, and they cannot see the bottom. The law bears Benford's name, not Newcomb's. This is itself a pattern with a name. In 1980, the statistician Stephen Stigler published what he called Stigler's Law of Eponymy, which states that no scientific discovery is named after its original discoverer. Stigler, in a move of deliberate irony, credited the idea to the sociologist Robert K. Merton. The law of misattribution is itself misattributed. Ted Hill, the mathematician who would later provide the deepest proof of Benford's law, put it plainly in American Scientist in 1998. Newcomb's article went unnoticed, and 57 years later, General Electric physicist Frank Benford, apparently unaware of Newcomb's paper, made exactly the same observation. Quote, a 2024 arXiv paper by Mir and Osluz traced the moment the misattribution became permanent to Ralph Ramey's 1976 formalization in the American Mathematical Monthly, where the phrase Benford's Law first appeared in print as a formal eponym. After that, the name stuck. Newcomb was erased twice, once by his own errors in difference, and once by a citation convention that nobody bothered to correct. But the naming injustice, as real as it is not the part of this story that should keep you up at night. The part that should keep you up at night is the mathematics underneath. Because while Newcomb and Benford both observed the pattern and Benford confirmed it empirically, neither of them could explain why it works. Neither could anyone else for another 57 years. And the explanation, when it finally came, only made the mystery deeper. The formula itself is deceptively simple. The probability that the leading digit of a naturally occurring number is d equals log base 10 of the quantity 1 plus 1 over d. Plug in the digits 1 through 9 and you get the full distribution. For d equals 1, that gives you log of 2, which is 0.301 or 30.1%. For d equals 2, log of 3 over 2 17.6%. For 3, 12.5. For 4, 9.7. For 5, 7.9. For 6, 6.7. For 7, 5.8. For 8, 5.1. And for 9, log of 10 over 9, 4.6%. The curve drops steeply. The digit 1 is 6.5 times more likely to lead a number than the digit 9. And this is not just a first digit phenomenon. The second digit has its own distribution, running from about 12% for 0 down to about 8.5% for 9. The asymmetry fades as you move to the third and fourth digits, converging toward the uniform 10% you would naively expect. By the fourth significant digit, the distribution runs between about 10.02% and 9.98%. But the first digit is wildly non-uniform, and that non-uniformity is what makes the law both powerful and strange. There is a clean geometric intuition behind the formula that most explanations never give you. So let me try. Imagine a ruler, but instead of being marked off in equal increments of 1, 2, 3, 4, it is marked off logarithmically. On this ruler, the distance from 1 to 2 is the same as the distance from 2 to 4, which is the same as the distance from 4 to 8. Each doubling takes up the same amount of space. This means the interval from 1 to 2, where every number has a leading digit of 1, occupies about 30.1% of the total length of the ruler between 1 and 10. The interval from 9 to 10, where every number has a leading digit of 9, occupies only about 4.6%. Now imagine dropping a pin onto this ruler at random. The probability that the pin lands in the 1 to 2 zone is about 6.5 times higher than it landing in the 9 to 10 zone. Just because of geometry, the low digits take up more room on a logarithmic scale. And here is why that matters. Nature does not count linearly. Nature multiplies. Populations do not grow by adding a fixed number of people each year. They grow by a percentage. Stock prices do not rise by a fixed number of cents each day. They rise by a percentage. Radioactive atoms do not decay in fixed batches. They decay at a fixed rate proportional to how many are left. River systems, city sizes, earthquake magnitudes, even the distribution of income across a population. All of these arise from processes where the amount of change is proportional to the current amount. That proportional character means the data is distributed logarithmically, and logarithmically distributed data projected onto the leading digit gives you Benford. That explanation is correct. As far as it goes, it tells you the mechanical reason the law works. Logarithmic processes produce logarithmic distributions, and logarithmic distributions produce Benford's digit pattern. But it pushes the real question back one level. Why are so many natural processes logarithmic? Why is the universe built out of multiplication and compounding rather than addition and linear growth? That is the question nobody has answered. That is the open mystery. And the person who got closest was a man named Theodore P. Hill. Hill's biography connects to this story in a way that matters, because he is not the kind of person you expect to find at the center of a mathematical mystery. He graduated from the United States Military Academy at West Point. He served as a combat officer. Then he turned to mathematics, eventually joining the faculty at Georgia Tech, and spent decades working on the foundations of probability theory and Benford's law. He's disciplined, precise, and patient, in the way that people who have been trained for combat tend to be patient. He does not rush. He does not hand wave. And when he says something cannot be explained, he means it in the strongest possible sense. In 1995, Hill published 2 papers that changed the field. The first, Base Invariance Implies Benford's Law, appeared in the Proceedings of the American Mathematical Society, Volume 123, Number 3, pages 887 through 895. The second, A Statistical Derivation of the Significant Digit Law, appeared in Statistical Science, Volume 10, Number 4, pages 354 through 363. Together, they represent the deepest mathematical analysis of Benford's law ever produced, and they also represent the clearest articulation of what we still do not know. I want to walk through what Hill proved because it is the kind of result where the setup is everything. If you do not understand what was expected, you cannot feel the shock of what was found. Imagine you have a jar, and inside that jar are slips of paper, and on each slip is a probability distribution. One slip says, draw from a uniform distribution between 0 and 1,000. Another says, draw from an exponential distribution with mean 50. Another says, draw from a power law with exponent 2. Another says, draw from a normal distribution with mean 100 and standard deviation 30. The distributions are different. They cover different ranges. They have different shapes. Some are symmetric, some are skewed, some are bounded, some are not. Now you reach into the jar, pull out a random slip, draw a random number from whatever distribution is written on it, and write down the leading digit. You put the slip back, you reach in again, pull another slip, draw another number, write down the leading digit. You do this thousands of times. What would you expect the leading digits to look like? If you think about it carefully, there is no obvious reason they should follow any particular pattern. The distributions are different, the ranges are different, the shapes are different. You might expect the digits to be messy, noisy. Dependent on which distributions happen to be in the jar, you might expect that if you change the distributions, you would get a different digit pattern. Here is what Hill proved. No matter what distributions are in the jar, no matter how many or how few, no matter what shapes they have, the leading digits of the combined sample converge to Benford's law. Every single time. The more distributions you mix, the closer you get. The result is universal. It does not depend on the specific distributions. It depends only on the mixing. Hill called this a kind of central limit theorem for significant digits, and the analogy is precise. The classical central limit theorem says that if you add up enough independent random variables, the sum converges to a bell curve, regardless of the underlying distributions. Hill showed that if you sample from enough independent random distributions, the leading digits converge to Benford's law regardless of the underlying distributions. Both results say the same thing at a structural level. Mixing washes out the details and produces a universal pattern. This is why Benford's original grab bag of rivers and baseball statistics and Reader's Digest numbers fits the law so well. He was not testing 20 clean distributions. He was mixing 20 different processes. Rivers arise from erosion and hydrology. Baseball statistics arise from human performance. Reader's Digest numbers arise from editorial choices about what numbers to print. These processes have nothing in common, but mixing them together produces Benford. because mixing is exactly the condition under which Hill's theorem guarantees the logarithmic digit distribution must emerge. And this, by the way, resolves a confusion that has plagued popular discussions of the law for decades. People often ask, does the law apply to my specific dataset? And the answer is, it depends. Many individual distributions do not follow Benford. Human heights do not. IQ scores do not. Telephone area codes do not. But once you start mixing datasets, once you start combining numbers from different sources and different processes, Benford emerges whether you want it to or not. The law is not a property of any particular dataset. It is a property of mixing. It is what the universe produces when it throws many different processes together, which is what the universe always does. But here is where most explanations stop. And here is where the real mystery begins. Hill's theorem tells you that Benford's law is mathematically inevitable if you accept two premises. First, that data is drawn from a mixture of distributions. Second, that those distributions are themselves drawn without bias toward any particular scale. The first premise is obviously true of real-world data. The world is messy. Numbers come from everywhere. The second premise is another way of saying that the data is scale invariant, meaning it does not change its fundamental character when you multiply everything by a constant. Lengths measured in kilometers produce the same digit pattern as lengths measured in miles or furlongs or light years. Prices in dollars produce the same pattern as prices in euros or yen. Scale invariance is the engine, and I want to make sure you understand what scale invariance actually means, because it is the most important concept in this entire story, and it is the concept that almost everyone who misapplies Benford's law gets wrong. Scale invariance means the data looks the same regardless of what units you measure it in. If you take all the rivers in the world and measure their lengths in kilometers, the first digit distribution follows Benford. Now convert every measurement to miles. The first digit distribution still follows Benford. Convert to furlongs, to nautical miles, to light seconds. Still Benford. The distribution does not care about your units. It does not care whether you are measuring in inches or parsecs. The pattern survives any multiplication by a constant, because multiplication by a constant is just a change of units. This is a profoundly strange property if you think about it carefully. Most things change when you change the scale. If you take a set of numbers and multiply them all by 2, the mean doubles, the median doubles, the standard deviation doubles. Everything changes. But the first digit distribution does not change. It is invariant under scaling. It is the same at every magnification. Roger Pinkham proved in 1961 in the Annals of Mathematical Statistics, Volume 32, Number 4, pages 1223 through 1230, that this invariance property uniquely determines the distribution. His theorem says that any probability distribution on the leading significant digit that is invariant under multiplication by a positive constant must be the Benford distribution. There is no other option. If your data is scale invariant, the logarithmic digit distribution is not one possible outcome. It is the only possible outcome. The intuition behind this is actually quite beautiful, and I want to give it to you, because it almost never appears in popular accounts. Imagine you are standing on a number line that stretches from 1 to infinity. You are at some position, and you are looking at the leading digit of that position. Now imagine someone grabs the entire number line and stretches it, multiplying every position by some factor. everything shifts. Numbers that were in the 1 to 2 range might end up in the 3 to 4 range. Numbers that were in the 5 to 6 range might end up in the 10 to 20 range. But if the distribution of your starting positions was Benford to begin with, the distribution of your ending positions is also Benford. The stretching does not disturb the pattern. It is the only pattern that survives arbitrary stretching. Every other digit distribution would be distorted by a change of scale. Benford alone is preserved. It is, in a precise mathematical sense, the fixed point of scaling. It is the digit distribution that the universe converges to when it does not favor any particular scale. Hill proved that base invariance, meaning the law holds in any number base, not just base 10, leads to the same conclusion. The mathematics is airtight. If your data is scale invariant, Benford follows necessarily. But why is so much data scale invariant? I want you to sit with that question for a moment, because it is the question that every mathematician who has spent serious time on Benford's law will eventually point you to. And none of them have an answer. Not a vague sort of answer. Not a hand-wavy argument. No answer. Rachel Fuster of the University of Auckland called it a tantalizing and mysterious law of nature in The American Statistician in 2009. William Feller, one of the most important probabilists of the 20th century, proposed an explanation in 1966 based on what he called regularity and large spread. The idea was that any data set whose values span many orders of magnitude and are distributed regularly should follow Benford. Berger and Hill tested this argument rigorously and showed it was fallacious. They wrote that Feller's argument fails for any reasonable definitions of regularity and spread. The conditions Feller described are neither necessary nor sufficient for Benford. The argument sounds plausible. It does not work. Warren Weaver dismissed the whole thing in his 1963 book, Lady Luck, as a built-in characteristic of our number system. Hill called that unsatisfying, and it is unsatisfying because the law is not just about the number system, it is about the world. River lengths actually follow the distribution. Earthquake depths actually follow it. Stock prices actually follow it. The pattern is not in the mathematics alone. It is in the data. It is in reality. And then, in 2011, Hill and Arno Berger published the paper I mentioned at the beginning, No Simple Explanation in Sight for Mathematical Gem. In the Mathematical Intelligencer, Volume 32, Issue 4, they surveyed every proposed explanation. They tested every heuristic argument. And they concluded, in language that could not be more precise, there is no known back-of-the-envelope argument, not even a heuristic one, that explains the appearance of Benford's law across the board. That was not false modesty. That was the considered verdict of the two people who had done more to put Benford's law on rigorous mathematical foundations than anyone alive. They spent decades on this problem. They proved the deepest theorems in the field, and they wrote a paper saying they could not explain it. And here is a fact I want you to hold in your mind while we move into the next part of this story. We are about to talk about how this unexplained law is used to put people in prison. The forensic applications are real, the convictions are real, the law works, and the people who proved it works are the same people telling you they cannot explain why. Before we get there, I need to clear up a misconception, because it shows up in almost every popular explanation of Benford's law. And it is wrong. People hear the digit 1 is more common, and they think the law means small numbers appear more often in nature. That is not what it says. The number 100 billion starts with 1 just as surely as the number 1.3. Benford's law is not about magnitude. It is about the first significant digit, regardless of how many zeros follow it. The reason is purely about the spacing of numbers on a logarithmic scale. On that scale, the interval from 1 to 2 occupies the same proportion of space as the interval from 10 to 20, or from 100 to 200, or from 1 billion to 2 billion. The law is about geometry, not size. And getting this wrong leads to exactly the kind of misapplication we are going to see later when we talk about elections. But first, I want to show you something that makes the law feel less like a statistical curiosity and more like something woven into the fabric of arithmetic itself. Take the Fibonacci sequence. 1, 1, 2, 3, 5, 8, 13, 21, 34, 55, and so on, each number the sum of the two before it. This sequence shows up everywhere in nature. Pinecone spirals, sunflower seed patterns, the branching of trees. But here is something about it that almost nobody mentions. Among the first 1,000 Fibonacci numbers, 301 of them start with the digit 1. The Benford prediction for a dataset of 1,000 numbers is 301.0. The fit is exact to within a single digit. This is not a coincidence. And the reason it is not a coincidence reveals something deep about the mathematical structure underneath. The Fibonacci numbers grow geometrically. Their ratio converges to the golden ratio phi, which is approximately 1.61803. By Binet's formula, the nth Fibonacci number is approximately phi to the n divided by the square root of 5. The logarithm base 10 of phi is approximately 0.20898, which is irrational, and by a result in number theory called Weyls' equidistribution theorem, any sequence whose logarithms have an irrational spacing is guaranteed to be Benford in the limit. The fractional parts of the logarithms spread out uniformly across the interval from 0 to 1, and that uniform spread is mathematically identical to Benford's digit distribution. The same argument works for powers of 2, powers of 3, powers of any integer that is not itself a power of 10, and for factorials. Even the Collat sequence, one of the most stubbornly unsolved problems in mathematics, produces Benford distributed values. Kontorovich and Miller proved this in Acta Arithmetica in 2005. The law is not something that happens to apply to a few convenient datasets. It is built into the way numbers grow under multiplication. It is structural, and the precision of the fit is eerie. Among the first billion powers of 2, exactly 301,029,995 of them start with 1. The Benford prediction is 301,029,995.6. The error is less than one number in 300 million. That is not a rough approximation. That is the kind of fit you expect from a fundamental law, not from a statistical tendency. The law is not approximate. It is not a rough tendency. It is a precise mathematical fact about how numbers behave when they grow multiplicatively. And it is not confined to pure mathematics. In 2010, Malcolm Sambridge, H.R. Wojciechowski, and Andrew Jackson at the Australian National University published a paper in Geophysical Research Letters, testing Benford's law against data from the natural sciences. They tested 248,915 global earthquake depths recorded by the International Seismological Center. Benford. They tested seismic P-wave travel times through the Pacific Mantle. Benford. They tested the spherical harmonic coefficients of Earth's geomagnetic field. Benford. They tested pulsar rotation frequencies from the Australia Telescope National Facility Catalogue. Benford. They tested 1,452 photon fluxes from the Fermi Space Telescope. Benford. They tested 987 infectious disease case counts reported to the World Health Organization. Benford. Every single natural dataset they tested followed the law, and it extends beyond the physical sciences. Jen Golbeck, a professor at the University of Maryland, tested social media data. She published a paper in PLOS One in 2015 showing that the friend counts of users on Facebook, Twitter, Google+, Pinterest, and LiveJournal all follow Benford's law. All 5 platforms, all Benford. Then in 2019, she published a follow-up in First Monday showing that bot accounts, automated fake accounts, violate Benford on the friend counts of their followers. Real social networks produce Benford-compliant friend distributions. Fake ones do not. She had turned Benford's law into a bot detector. The same pattern that governs earthquake depths and river lengths also governs how real human social networks organize themselves. And it breaks when the network is artificial. Nigrini himself tested the populations of all 3,141 counties in the 1990 United States Census. Benford. He tested the interest received line item from the IRS 1978 individual tax model file. 157,518 observations. Benford. He tested accounts payable data from a Fortune 500 company. Benford. Eduardo Ley, in a 1996 paper in The American Statistician, tested daily log returns of the Dow Jones Industrial Average from 1900 through 1993 and the S&P 500 from 1926 through 1993. Both followed Benford with high precision. The universality is the point. This is not a law that applies to one kind of data. It applies to earthquake depths and stock prices and Facebook friend counts and pulsar rotation frequencies and census data and the Fibonacci sequence and the powers of 2. The numbers come from completely unrelated processes. Earthquakes have nothing to do with Facebook. Pulsars have nothing to do with the Dow Jones. River lengths have nothing to do with radioactive half-lives, but they all follow the same digit distribution. They all prefer the digit 1 by the same amount. They all obey the same formula that Newcomb wrote down in 1881. And that universality is the reason this matters. The reason it stops being a curiosity and starts being something that should genuinely unsettle you. Because it means human beings are embedded in a universe that generates numbers according to a specific, predictable pattern. A pattern that humans cannot replicate when they try to invent numbers from scratch. Because humans cannot do this. Humans cannot generate numbers that follow Benford's law without knowing the law exists and deliberately constructing numbers to match it. And even when they know about it, they almost always get it wrong. The human brain does not think logarithmically. It thinks linearly. When asked to pick a random number, people spread their choices roughly evenly across the available digits. They avoid repeating digits. They avoid patterns. They gravitate towards certain favorites, especially 7. And the result is that fabricated data has a digital fingerprint that is detectably different from natural data. In 1992, a South African chartered accountant named Mark Nigrini figured out how to turn that fingerprint into a forensic tool. Nigrini was born in Cape Town. He trained as a chartered accountant in South Africa, then moved to the United States to pursue a doctorate in accounting at the University of Cincinnati. His dissertation, submitted in 1992, was titled "The Detection of Income Tax Evasion Through an Analysis of Digital Distributions." The premise was simple and devastating. When a number arises from a natural process, its leading digits follow Benford's law. When a human being invents a number, the leading digits follow something closer to a uniform distribution, or they cluster around psychologically preferred digits. And that mismatch, that gap between what nature does and what humans do, is statistically detectable. Nigrini distinguished between what he called planned evasion and unplanned evasion. Planned evasion is when a taxpayer maintains false records throughout the year, creating a consistent but fraudulent paper trail. Unplanned evasion is when a taxpayer sits down at filing time and invents numbers. The unplanned evader is the one who gets caught by Benford because they are generating numbers from their imagination rather than from economic reality, and their imagination does not produce the logarithmic curve. He built a suite of statistical tests around this insight. The first digit test checks whether the overall distribution of leading digits matches Benford's theoretical percentages. If you have a large dataset of financial transactions and the digit 1 shows up as a leading digit 22% of the time instead of 30.1%, something may be wrong. But the first digit test is a blunt instrument. It tells you something is off. It does not tell you where. The first 2-digit test is where it gets forensically powerful. This test breaks the data into 90 bins from 10 through 99 and checks each bin against its Benford prediction. A spike at a particular 2-digit combination is a red flag. If a company's expense reports show an unusual number of transactions with amounts starting with 49, that means someone is writing checks for amounts just under 5K. And the reason someone would do that is because $5,000 is a common threshold above which a second signature or additional approval is required. Threshold gaming shows up in the first 2-digit test as a spike just below the threshold value. You can literally see the fraud in the shape of the distribution. The summation test works differently. Instead of counting how many transactions start with each 2-digit combination, it sums the dollar amounts. In a clean dataset, the total dollar value contributed by each first 2-digit group should be roughly equal. If one group is disproportionately large, it means a few very large transactions are dominating that group, which is exactly what you would expect if someone is fabricating large entries. And Nigrini's preferred metric for measuring overall compliance is not the chi-squared statistic, which statisticians normally use for goodness of fit tests, but the mean absolute deviation, or MAD. The reason is practical. Chi-squared is sensitive to sample size. If you have 1 million transactions, chi-squared will reject Benford even if the deviations are trivially small. MAD does not have this problem. It measures the average absolute difference between the observed and expected proportions, and its magnitude stays interpretable regardless of how much data you have. Nigrini's thresholds, published in his 2012 Wiley book, are clean and specific. For first-digit tests, a MAD between 0 and 0.006 is close conformity. Between 0.006 and 0.012 is acceptable. Between 0.012 and 0.015 is marginal. Above 0.015 is non-conformity. Above that line, you have a problem. The first major criminal case came in 1993, only a year after Nigrini completed his dissertation. In the state of Arizona, a manager in the state treasurer's office named Wayne James Nelson issued 23 fraudulent checks to a bogus vendor, attempting to divert nearly $2 million. His defense at trial was that he had been conducting an unauthorized test of weaknesses in a new computer system. The numbers told a different story. Over 90% of the 23 check amounts began with the digits 7, 8, or 9. In the natural dataset of financial transactions, those three digits combined should account for roughly 16% of leading digits, not 90. The distribution was the exact inverse of Benford's law. Nelson had invented amounts the way humans invent amounts, clustering them in the high digits because high digits feel more random and more plausible for large check amounts. He was spreading the digits around, doing what his brain told him randomness looked like, and his brain was wrong. Of the 160 individual digits used in those 23 check amounts, the digit 9 appeared 26 times, the digit 8 22 times, the digit 7 22 times, and the digit 1 only 19 times. In a natural dataset, the digit 1 would dominate. In Nelson's fabricated dataset, it was barely present. He was convicted. The case, State of Arizona v. Wayne James Nelson, CV 92 to 18841, became the first clean precedent for Benford's law in an American courtroom. And if that were the only case, this would be an interesting footnote in forensic accounting. But then, the applications started accumulating. In 2005, Nigrini published a paper in the Review of Accounting and Finance analyzing earnings reports from the period surrounding the Enron and Arthur Andersen collapse. He documented what he called a marked discontinuity in reported earnings per share around zero. Companies were manufacturing small positive earnings rather than reporting small losses, because the difference between reporting a gain of 1 cent per share and reporting a loss of 1 cent per share is, in terms of stock price impact, enormous. The digit distributions around the zero threshold were not natural. They were curated. Enron's own figures showed, in Nigrini's words, a strong tendency towards making financial thresholds. This was not a Benford-driven prosecution. It was a Benford-driven confirmation after the fact. Then there is the case that haunts this entire story. Bernie Madoff ran the largest Ponzi scheme in history, with stated client liabilities at collapse of approximately $50 billion, later revised by federal prosecutors to $64.8 billion. The famous whistleblower, Harry Markopolos, submitted a memo to the Securities and Exchange Commission in 2005 with the title, "The World's Largest Hedge Fund is a Fraud." Markopolos built his case using auctions volume impossibilities and mosaic analysis, not Benford's law, and claims that he used Benford as a primary tool are overstated. But post-collapse analyses of the Fairfield Century Feeder Fund's monthly returns, spanning December 1990 through October 2008, showed something that should have been caught. A chi-squared test of the leading digits gave a p-value of 0.0453, which is below the conventional 5% significance threshold. A discrete Kolmogorov-Smirnov test focused on the 1990s returns alone gave a p-value of 0.0021. The numbers were deviating from Benford. The deviation was statistically significant. It had been statistically significant for years. The auditor for Madoff's fund was a one-man firm called Freeling and Horowitz, operating out of a 13 by 18-foot office in a strip mall in suburban New York. I want to make sure the weight of that lands properly. A digit frequency test, something you could run in a spreadsheet in 15 minutes, could have flagged Madoff's returns as anomalous nearly a decade before the scheme collapsed. Nobody ran it. The SEC received warnings and did not act. The auditor did not audit. And $50 billion evaporated. You would think someone would have said something. Nobody did. And the pattern of nobody looking extends to entire nations. In 2011, 4 German researchers named Rausch, Gotcha, Engel, and Brala published a paper in the German Economic Review with the title Fact and Fiction in EU Governmental Economic Data. They applied Benford's first-digit test to the macroeconomic data that eurozone countries submit to Eurostat under the Stability and Growth Pact, the data that determines whether a country is meeting its fiscal obligations. The dataset covered 1999 through 2009, a full decade of self-reported government statistics. Their finding was blunt. The data reported by Greece shows the greatest deviation from Benford's law among all Euro states. Romania, Latvia, and Belgium also flagged, but Greece was the worst. Greek deficit figures were subsequently revised from 5% of GDP to 7.7% for 2008. The 2009 planned deficit of 3.7% was ultimately restated to 15.4%. That is not a rounding error. That is a factor of 4 revision in a number that entire bond markets relied on. The numbers Greece had been reporting to Brussels were not natural numbers. They were constructed numbers. And a digit frequency test said so before the sovereign debt crisis blew apart the eurozone and devastated Greek society for a decade. The most thoroughly documented forensic success is the Zenetics case. Kevin L. Lawrence ran an investment scheme through a company called Zenetics Incorporated, defrauding approximately 5,000 investors across 36 states of roughly $91 million. Forensic accountant Darrell Dorrell, working with the SEC receiver, compiled a list of more than 70,000 numbers representing checks and wire transfers and ran Benford's law as an initial screen. The digit distributions flagged the web of shell companies that Lawrence had constructed to move money between entities. On November 25, 2003, United States District Judge Marsha J. Peckman sentenced Lawrence to 20 years in federal prison and ordered restitution of $91,644,845.86, the largest restitution order in Washington state history at the time. Dorrell later described the case on Radiolab, explaining how the initial Benford screen had pointed investigators toward the shell company network they might otherwise have missed. And the applications have extended beyond financial fraud into scientific fraud, which raises a whole separate set of unsettling questions. In 2007, Andreas Diekmann at the Swiss Federal Institute of Technology published a paper in the Journal of Applied Statistics titled "Not the First Digit." His finding was counterintuitive. When researchers fabricate data, they often get the first digit distribution roughly right, either by accident or because they have heard of Benford's law. But they almost always fail on the second, third, and fourth digits. The downstream digits are where the fabrication shows. Diekmann recommended testing beyond the first digit for any dataset suspected of containing invented results. This has since been applied retrospectively to several high-profile cases of scientific fraud. The Diederik Stapel fabrication scandal in social psychology and the James Hunton data fabrication case in accounting research have both been analyzed using Benford-based digit tests, with results consistent with data manufacture. The implication is uncomfortable. Scientific data, the data we build public policy on, the data we use to approve drugs and design bridges and set environmental regulations, can be tested for fabrication using digit analysis. The tool exists, it works, but it is not routinely applied to published datasets before they enter the scientific record. There is no standard Benford audit at the point of peer review. The screening tool exists and it is sitting unused while fabricated results circulate in the literature. The pattern here is consistent. Natural data follows Benford. Fabricated data does not. The gap between the two is statistically detectable, and forensic accountants, auditors, and regulators have been using that gap to catch criminals for 3 decades. The tool works. The convictions hold. Benford's law is admissible under the Daubert standard for scientific evidence in federal courts. The European Anti-Fraud Office hosted an international Benford conference in Stresa, Italy in July 2019. Nigrini's methods are standard curriculum at the Big Four accounting firms. But here is the thing that I personally think is underappreciated and that nobody in the forensic accounting world seems to want to talk about openly. We are convicting people using a mathematical law whose deepest proponents have publicly stated they cannot explain from first principles. The tool works. We know it works empirically. We can prove that it must work under certain mathematical conditions, but we cannot derive those conditions from any deeper principle. We cannot explain why the universe produces numbers this way. We just know that it does, and that humans do not, and we treat that gap as evidence of criminal intent. Think about that for a moment. Really think about it. In a criminal trial, the prosecution must prove its case beyond reasonable doubt. The evidence must be grounded in methods that are scientifically validated and generally accepted. Benford's law passes this standard. It is scientifically validated. The theorems are proven. The empirical record is overwhelming. The method is generally accepted by the forensic accounting community. It is taught, published, peer-reviewed, and admissible. Every part of the legal and scientific infrastructure says this tool is legitimate. But the philosophical foundation is something else entirely. We are using a law of nature that we cannot explain. We are measuring the gap between what the universe does with numbers and what a human being does with numbers. And we are calling that gap evidence of intent to deceive. And the reason the gap exists, the reason nature follows a logarithmic digit distribution in the first place, is a question that has been open for 145 years and that the leading mathematicians in the field have publicly declared they cannot answer. I am not saying the convictions are wrong. I believe the tool works. The evidence that it works is overwhelming. Nelson was guilty. Lawrence was guilty. The Greek data was fabricated. The Madoff returns were not real. The tool correctly identified all of them, but the fact that we are using it without understanding why it works says something about the relationship between human civilization and the patterns underneath it. We build on patterns we can detect but cannot explain. We build legal systems on them. We build financial systems on them. We audit governments with them. And then we go home and never think about the fact that the foundation is a mystery. And then think about what happens when the law is applied by people who do not understand its preconditions. Because the same mathematical precision that makes Benford powerful also makes it dangerous in the wrong hands. And we do not have to imagine how that goes wrong. We have a case study, and it is ugly. On June 12, 2009, Iran held a presidential election. The incumbent, Mahmoud Ahmadinejad, claimed victory with 63% of the vote. Protests erupted. The opposition alleged fraud. International observers expressed concern. And within 2 weeks, a political scientist at the University of Michigan named Walter Mebane circulated a statistical analysis that would become the most cited application of Benford's law to election data ever produced. Mebane is important to this story, and I want you to understand who he is, because 14 years later, his entire body of work would be ignored by the people who needed it most. He holds a PhD from Yale, earned in 1985. He has a Harvard AB magna cum laude. He is a professor of political science and statistics at Michigan. He has been publishing on election forensics since the mid-2000s, and he had been saying, clearly and repeatedly, in paper after paper since 2006, something very specific about Benford and elections. The first digit test does not work on precinct-level vote counts. It never has, it never will. The reason is structural. Precinct-level vote counts do not span enough orders of magnitude for first-digit Benford to apply. Remember, Benford's law requires data that ranges across multiple orders of magnitude, data where the smallest values are 10 or 100 or 1,000 times smaller than the largest values. Precinct-level vote counts in a typical American election range from a few hundred to a few thousand. That is barely one order of magnitude. The logarithmic spread that produces Benford's digit pattern simply does not exist. In this data, what Mebane developed instead was a second-digit Benford test, which he called the 2BL test. The second-digit distribution under Benford's law is much flatter than the first-digit distribution, running from about 12% for 0 down to about 8.5% for 9. And crucially, the second digit is appropriate for data that spans a narrower range. Mebane argued, with theoretical and empirical support, that the 2BL test is appropriate for precinct-level vote counts under certain assumptions about the data-generating process. He applied the 2BL test to the Iranian results. The fair election null hypothesis was rejected well beyond 99% confidence for Ahmadinejad, Karabi, and Rezai. 81 out of 320 towns were flagged as statistical outliers, overwhelmingly in Ahmadinejad's favor. A multinomial regression using the 2005 election as a baseline flagged 91 additional, poorly fitting towns. Mebane's conclusion was measured but unambiguous. The patterns strongly suggest there was ballot box stuffing. But what makes the Iranian case the gold standard in electoral forensics is not any single test. It is the convergence. Multiple independent teams using completely different methods applied to different features of the data, conducted at different institutions in different countries, all pointed in the same direction within weeks. Budowin Rukoma at Nicolaus Copernicus University in Torun, Poland, posted a first-digit analysis on ArcSiv, paper number 0906-2789, within 4 days of the vote. His method was different from Mebane's. He was looking at the first-digit distribution of vote counts for individual candidates in individual towns. For the candidate Mehdi Karoubi, who had been a major figure in Iranian reformist politics and a serious contender in 2005, 41 vote counts began with the digit 7. The expected number under Benford was 21.2. That is nearly double the expected frequency. The probability of a deviation that large occurring by chance was less than 0.0015, or roughly 1 in 650. That paper was later published in the Journal of Applied Statistics, Volume 41, Number 1, in 2014. Bernd Weber and Alexandra Skako, both political scientists, took a completely different approach. Their Washington Post op-ed on June 20, 2009, "The Devil is in the Digits," tested the last digits and second to last digits of vote counts. This is an entirely different feature of the data than what Mebane or Rokema tested. In a fair election, the last digit of a vote count should be uniformly distributed. There is no physical or mathematical reason for a real vote count to end in 7 any more often than it ends in 3 or 6. But in the Iranian results, the digit 7 appeared in the final position 17% of the time, almost double the expected 10%. They also tested the frequency of non-adjacent digit pairs in the last 2 positions. In a fair election, adjacent pairs like 3-4 or 6-7 should appear roughly 30% of the time. Non-adjacent pairs like 2-7 or 1-9 should appear roughly 70%. The Iranian results showed only 62% non-adjacent pairs, significantly below the expected 70, suggesting that whoever manufactured the numbers was unconsciously avoiding gaps between consecutive digits, a known signature of human number generation. Their combined p-value was less than 1 in 200. Their formal paper, developing the methodology in full, appeared in Political Analysis, Volume 20, Number 2, in 2012. And the Chatham House report, authored by Ali Ansari with Daniel Berman and Thomas Rintoul, and published on June 2009, used no digit tests at all. It was pure demographic analysis. They documented that in the province of Mazandaran, the reported turnout appeared to exceed 100% of eligible voters. In Yazd province, same thing. Turnout over 100% is not a statistical anomaly. It is a mathematical impossibility. And Karoubi, who had won over 55% of the vote in his home province of Loristan in 2005, allegedly received only about 5% in 2009. A 50-point collapse in a candidate's home region is not impossible. But combined with everything else, it became one more data point in a pattern that was becoming undeniable. No single test was conclusive on its own. Mebane's second-digit test alone would not prove fraud. Rukema's first-digit anomaly alone might have an innocent explanation. Weber and Skako's last-digit test alone could be a statistical fluke. The Chatham House demographic impossibilities alone might have an administrative explanation. But 4 independent analyses, using 4 different methods, testing 4 different features of the data, conducted by 4 different research groups at 4 different institutions, all pointed in the same direction. That kind of convergence does not happen by accident. This was Benford's law and its related digit tests, used correctly, used by people who understood the mathematical preconditions, applied with the right test to the right data at the right level of confidence, used as part of a mosaic, not as a standalone proof. And then, November 2020 arrived and everything went sideways. Within days of the United States presidential election, charts began circulating on social media, claiming to show that Joe Biden's vote counts in Milwaukee, Chicago, Allegheny County, and Fulton County violated Benford's law, while Donald Trump's counts did not. A GitHub repository compiled the analysis. The charts were shared millions of times across Twitter, Facebook, Reddit, and Parler. The implication was explicit and unambiguous. The numbers prove fraud. Benford's law catches liars, and Biden's numbers look like lies. The analysis was wrong. Not debatably wrong. Not arguably wrong, mathematically wrong, wrong in a way that Mebane had predicted and warned about in published academic papers for 14 years. Let me walk through exactly why, because the error is instructive and it connects directly to the deeper mystery about the law itself. In Chicago, the Biden-Harris ticket averaged approximately 82% of the vote, in precincts of roughly 1,000 voters each. That means Biden's vote counts in most precincts clustered around 820. The leading digits of those counts were therefore 3, 4, 5, 6, 7, and 8. The digit 1 was rare because Biden's counts in Chicago precincts were almost never in the 100s. They were in the 800s. Meanwhile, Trump's vote counts in the same precincts clustered around 180. His leading digit was 1, almost always. So when you plot the first digit distributions for both candidates, Biden's distribution looks non-Benford, with very few ones, and Trump's looks Benford compliant, with lots of ones. And if you do not understand why, it looks like proof. But it is not proof. It is arithmetic. A candidate who wins 90% of the vote in precincts of 500 will have counts clustering around 450. Their leading digit will be 4. A candidate who wins 10% of the same precincts will have counts clustering around 50. Their leading digit will be 5. A candidate who wins 30% will cluster around 150. Leading digit 1. None of this has anything to do with Benford's law. The first digit is determined by the product of precinct size and vote share, not by the honesty of the count. Mebane's working paper, circulated on November 10, 2020, was titled Inappropriate Applications of Benford's Law, Regularities to Some Data from the 2020 Presidential Election. His language was as precise as ever. It is widely understood that the first digits of precinct vote counts are not useful for trying to diagnose election frauds. The first digit is largely determined by the number of voters in each precinct. He ran his Bayesian forensics model, a far more sophisticated tool than first-digit Benford, on the flagged jurisdictions. Milwaukee came back at 0.9797 probability of no fraud, 0.018 probability of incremental fraud, 0.0023 probability of extreme fraud. The numbers were clean. Hill told Reuters that the application of Benford's law would not provide definitive evidence that fraud took place. Rukamer, who had correctly used first-digit Benford on the Iran 2009 data, called out the flaw explicitly. A major flaw in applying Benford's law to the Milwaukee results is that the logarithmic distribution is very narrow. Jen Golbeck, who had published peer-reviewed Benford work demonstrating that social media bot accounts violate the law on friend count distributions, wrote a detailed debunking. The Deckert, Mayakov, and Ordshuk paper, published in Political Analysis in 2011, had already shown that applying first-digit Benford to election data produces false positives 34% of the time and misses actual fraud 60% of the time. Their success rate, they wrote, is essentially equivalent to a toss of a coin. 14 years of published warnings, ignored. Every single one. I am going to say something here that I think the evidence supports strongly enough to state plainly. The 2020 Benford fiasco did more damage to the law's scientific reputation than any legitimate mathematical criticism in 140 years. A tool that actually works, that has actually convicted criminals, that has actually flagged fabricated data in published research and sovereign economic statistics, got permanently associated in the public mind with election conspiracy theories. And it happened because people who did not understand the mathematical preconditions treated a screening heuristic as a proof engine. They did not read Mebane, they did not read Deckard. They saw a chart that confirmed what they wanted to believe, and they shared it. And here is the part that connects back to the deeper mystery and that I still do not know how to think about. The election debacle does not just reveal political misuse, it reveals a genuine gap in our understanding of the law itself. We cannot derive from first principles which datasets should follow Benford and which should not. We know empirically that river lengths follow it and human heights do not. We know that stock prices follow it and lottery numbers do not. We know that populations follow it and IQ scores do not. We know that precinct-level vote counts do not. We can give post hoc explanations for each case. River lengths span many orders of magnitude and arise from multiplicative erosion processes. Human heights are bounded between roughly 150 and 200 centimeters and cluster around a mean. Stock prices grow multiplicatively. IQ scores are designed to have a fixed mean and standard deviation. Precinct vote counts are the product of precinct size and vote share, both of which are bounded and clustered. These explanations work case by case. But there is no general principle, no single criterion you can check that tells you in advance whether a new dataset will follow the law. There is no theorem that says dataset X will be Benford if and only if conditions A, B, and C are met. We are pattern matching. We are relying on experience and intuition and post hoc reasoning. And that is a profoundly uncomfortable position for a tool that is used in courtrooms and national audits and SEC investigations. This is the point where most popular explanations of Benford's law end. They tell you the law exists, they show you some applications, maybe they mention the election controversy, and they wrap up with something about how mathematics is beautiful and mysterious. I am not going to do that, because the mystery is not a cute footnote. It is the actual story, the real story, and it has not been resolved. The deepest mathematical result we have is Hill's 1995 theorem. It tells you that Benford emerges from mixing. It tells you that scale invariance forces the logarithmic distribution. It tells you that base invariance pins down the formula uniquely. The mathematics is rigorous, elegant, and complete, but it rests on a premise, scale invariance, that is itself an empirical observation about the world. And the question of why the world is scale invariant, why so many natural processes are multiplicative rather than additive, why growth rates are so often proportional to current size, that is not a mathematical question. It is a question about the structure of physical reality, and nobody has an answer. Terence Tao described the mechanism with his usual clarity. If a stock price starts at $100 and each day gets multiplied by a randomly chosen factor between 0.99 and 1.01. Then, over an extended period, the distribution of its price satisfies Benford's law with increasing accuracy. The logarithm of the price performs a random walk. By the classical central limit theorem, that random walk becomes approximately normally distributed, which means the price itself becomes approximately log normally distributed, which means its leading digits converge to Benford. The chain is clean. Multiplicative process, random walk in log space, normal distribution in log space, Benford in linear space. But the chain starts with a multiplicative process. And the question is why multiplicative processes are so prevalent in nature. Populations grow multiplicatively because birth rates are proportional to current population. Stock prices move multiplicatively because percentage returns are roughly independent of price level. Radioactive decay is multiplicative because the probability of decay per unit time is constant, regardless of how many atoms remain. River networks grow through multiplicative erosion and sedimentation processes. City sizes follow Zipf's law, which is closely related to Benford, because cities grow by proportional attachment, larger cities attracting migration in proportion to their current size. Earthquake energies span many orders of magnitude because fault mechanics involve cascading failures whose magnitudes are scale-free. The sizes of biological organisms within an ecosystem span orders of magnitude. Income and wealth distributions span orders of magnitude. The masses of astronomical objects span orders of magnitude. Each of these is a perfectly valid explanation for why that particular dataset follows Benford. But taken together, they point at something deeper. The universe's default mode of change appears to be proportional. Things grow in proportion to their current size. Things decay in proportion to their current amount. Things vary in proportion to their current value. Proportional change is not one option among many. It is the dominant mode, and that proportional character, when fed through the mathematics of logarithms and the central limit theorem, produces Benford's law as an inevitable downstream consequence. But why is proportional change the default? Why does the universe prefer multiplication over addition? That question has not been answered. Pietranero, Tossati, and Vespignani connected Benford's law to scale-invariant critical phenomena in statistical physics in a 2001 paper in Physica A, showing that the whole family of scaling laws, Benford, Zipf, Pareto, power law distributions, emerge from the same underlying principle of scale-free organization. But that is not an explanation. That is a description of the pattern at a higher level of generality. It is like saying, the reason this particular river flows downhill is because all rivers flow downhill. True, not helpful. Scale invariance explains Benford, and Benford is evidence of scale invariance. The argument is circular. The bottom has not been reached, and the family of scaling laws is itself so pervasive that it deepens the mystery rather than resolving it. Zipf's law says that in any large corpus of natural language, the frequency of a word is inversely proportional to its rank. The most common word appears roughly twice as often as the second most common word, 3 times as often as the third, and so on. Pareto's law says that the distribution of wealth in a society follows a power law, with a small number of people holding a disproportionate share. Power law distributions show up in the sizes of cities, the magnitudes of earthquakes, the number of citations received by scientific papers, the number of links pointing to websites, the sizes of forest fires, the frequency of family names, the areas of lakes, and the intensities of wars. All of these follow the same mathematical family. All of them are scale invariant. All of them are related to Benford through the logarithmic structure they share. What this means is that Benford's law is not an isolated oddity. It is one manifestation of a much larger pattern that runs through the entire observable world. The universe organizes itself according to scaling laws at every level, from the microscopic to the cosmic, from the biological to the economic, from the linguistic to the geological, and nobody can explain why. The pattern is too universal to be coincidental and too fundamental to be derived from anything simpler. It is not explained by any existing physical theory. It is not predicted by quantum mechanics or general relativity or thermodynamics. It is just there, sitting underneath everything, organizing the digits of every number that nature produces. And it organizes your life too. The amounts on your credit card statement follow Benford's law. The populations of the cities you have lived in follow it. The distances you have traveled follow it. The numbers in your tax return, if you did not fabricate them, follow it. You are embedded in a universe that generates numbers according to a pattern you were never told about, a pattern that was discovered 145 years ago and is still not explained. And every number you encounter in daily life carries the fingerprint of that pattern, whether you notice it or not. I spent an unreasonable amount of time reading about this. I read Newcomb's original 2-page paper. I read Benford's 22-page paper. I read Hill's proofs. I read Nigrini's forensic manuals. I read Mebane's election forensics papers. I read the 2011 No Simple Explanation paper twice. And I want to be honest about where I ended up. The mathematics is clean. The proofs are rigorous. The forensic applications work. The law catches criminals and flags fabricated data and identifies manufactured economic statistics. Every part of the machinery functions precisely as advertised. But underneath all of it, at the very bottom, is an empirical fact about the structure of reality that nobody has reduced to anything simpler. The universe generates numbers logarithmically. It prefers the digit 1. It has been doing this since before humans existed to notice, since before there were logarithm tables to wear out, since before anyone named it after the wrong person. And the people who know the most about it, the people who have spent decades formalizing it and proving its properties and pushing its applications into courtrooms and audit offices, are the most explicit about saying they cannot explain why. Hill and Berger in 2011. No simple explanation in sight. Fuster in 2009. A tantalizing and mysterious law of nature. Benford himself in 1938. Deeper among the roots of primal causes than our number system unaided can explain. 3 statements spanning 73 years, all saying the same thing. We found something. It is real. We cannot explain it. And the reason they cannot explain it is not that they have not tried hard enough, or that they need better tools, or that the answer is waiting in some paper that has not been written yet. The reason is structural. The explanation for Benford's law is scale invariance. The explanation for scale invariance is that natural processes are multiplicative. The explanation for why natural processes are multiplicative is that growth and decay in the physical world are proportional to current state, and the explanation for why proportional change is the default mode of nature is, as far as anyone can determine, that the universe is built that way. Full stop. There is nothing underneath. Every attempt to go one level deeper just restates the premise in different language. This is not the same as saying the law is unexplainable in principle. It is possible that someday someone will find a derivation that starts from something truly fundamental, something in information theory or thermodynamics or the structure of measurement itself, and shows that Benford must follow as a logical consequence. That would be a result worth celebrating. But no one has done it. And Hill and Berger, who have spent more combined years on this problem than anyone, believe it may not be possible. The law may be foundational in the way that certain axioms in mathematics are foundational. You cannot prove them from anything simpler because they are the simplest things there are. The digit 1 dominates natural data the way parallel lines never meet in Euclidean geometry. It is not derived, it is observed, it is confirmed, and it is left standing as a brute fact about the world. I want to come back to the people now, because I think the human dimension of this story has a weight that the mathematics alone cannot carry. And because the pattern of these lives mirrors the pattern of the mathematics in a way that I do not think is coincidental. Simon Newcomb, born in poverty in Nova Scotia, the son of a school teacher who could not afford to give him a proper education, ran from an abusive apprenticeship at 16, walked into American science with nothing but his own mind and a desperate need to find a place where that mind would be valued, became one of the most decorated scientists in the Western Hemisphere, won the gold medal of the Royal Astronomical Society, served as the first president of the American Astronomical Society, collaborated with Michelson on the speed of light, was promoted to Rear Admiral by an act of Congress, and somewhere in the middle of all of that, noticed that the front pages of a book of logarithms were more worn than the back, sat down, derived the formula, published it in 2 pages, and moved on. 1 citation in half a century. He died on July 11th, 1909, of bladder cancer, and was buried with military honors at Arlington National Cemetery. His daughter, Anita Newcomb McGee, founded the United States Army Nurse Corps. His only son died in infancy. His 2-page paper was forgotten. The man who ran from a fraud discovered a way to catch frauds, and nobody listened. Not for a year, not for a decade, for 57 years. Frank Benford, born in Johnstown, Pennsylvania, survived the catastrophic failure of the South Fork Dam as a 6-year-old child, grew up in a rebuilt town haunted by disaster, became a physicist, designed the optics for theater spotlights, spent years of his life meticulously collecting data on river basins and baseball statistics and Reader's Digest numbers and street addresses and molecular weights and star brightness and X-ray voltages, 20 datasets, 20,229 observations, because he needed to know whether the pattern was real or whether he was imagining it. He was not imagining it. He did not know about Newcomb. He thought he was the first. He wrote that the law pointed at something deep in the roots of reality, something beyond what our number system alone could explain. And he called numbers the poor part of life for symbols for living things. He died suddenly at home in Schenectady on December 4th, 1948, 5 months after retiring from General Electric. He was 65 years old. His son Harry became a professor of naval architecture at the University of Michigan. The law bears Frank's name and not Newcomb's, which is an injustice that has been documented and protested by mathematicians for decades without effect. But Benford did something Newcomb never bothered to do. He showed that the pattern was not a quirk of logarithm tables. It was a property of the world. Mark Nigrini, born in Cape Town, trained as a chartered accountant under the South African system, moved to the United States and wrote a doctoral dissertation at the University of Cincinnati that turned an obscure mathematical curiosity into a weapon that would be used to catch embezzlers and flag sovereign economic fraud. He visited Benford's son Harry in Ann Arbor in 1993. He built the MAD thresholds and the first two-digit test and the summation test that are now standard tools in every major accounting firm and forensic practice. He published the book that auditors keep on their desks. And he watched, in November 2020, as the law he had spent his entire career applying carefully and precisely was ripped from its mathematical context and paraded through social media by people who could not pass a first-year statistics exam. Nigrini did not discover the law. He did not prove the law. What he did was see the forensic implication that Newcomb had hinted at in 1881, and that nobody had acted on for 111 years. He built the bridge between pure mathematics and criminal justice, and he watched that bridge get set on fire by political actors who did not understand what they were standing on. Ted Hill, West Point graduate, combat veteran, Georgia Tech mathematician. He came to this problem from the military, which gives him a relationship to precision and rigor that is different from a typical academic. Hill does not speculate. He proves things, or he says he cannot prove them. And what he proved in 1995 was the deepest mathematical result in the entire 114-year history of the problem. His central limit theorem for significant digits shows that Benford's law is universal in the same way the bell curve is universal. It is the attractor. It is what you get when you mix enough independent sources. And then, in 2011, he co-authored with Arno Berger a paper whose title is the most honest sentence anyone has written about this subject. No simple explanation in sight for mathematical gem. A soldier who spent his career trying to capture a position, writing a paper that says, with complete precision, that the position has not been captured, that the flag is not planted, that the summit is still above them. Walter Mebane, educated at Harvard and Yale, spent 14 years publishing careful, precise, methodologically rigorous warnings about how Benford's law should and should not be applied to election data. He developed the 2BL framework. He built Bayesian forensics models. He presented at conferences. He published in peer-reviewed journals. He made the argument as clearly and as publicly as it could be made. And in November 2020, not one person who pushed the viral Benford charts cited his work. Not one. 14 years of explicit, published, freely available warnings, ignored in favor of a chart that looked persuasive to people who had never read a statistics paper in their lives. Mebane published his debunking within 3 weeks. Nobody who promoted the original misanalysis retracted. Nobody corrected. The damage was done, and it was permanent. These are the people, and the pattern of their lives mirrors the pattern of the law itself in a way that is difficult to dismiss. Someone discovers something true. It is ignored, or misattributed, or misapplied. Decades pass. The truth survives, because mathematical truth does not depend on human recognition to remain true. But the people who found it pay a cost, in credit, in recognition, in the slow corrosion of watching the wrong version of your discovery circulate while the right version sits unread behind a paywall. Newcomb published a formula and was erased. Benford confirmed it and received credit for a discovery that was not originally his. Nigrini built the forensic applications and watched the law get weaponized by people who could not define scale invariance if their freedom depended on it. Hill proved the deepest theorems and concluded that the explanation is still missing. Mebane published the warnings, and nobody listened until the damage was done. And underneath all of it, through all the misattributions and misapplications and missed opportunities and methodological controversies, the law itself just keeps working, silently, indifferently, without any need for human understanding or approval. The digit 1 keeps appearing 30% of the time, in earthquake catalogs and stock tickers and tax filings and census data, in the rotation frequencies of pulsar spinning in galaxies so far away that the light arriving at our telescopes left before the Earth existed, in the friend counts on social media platforms that did not exist 15 years ago, in the molecular weights of compounds synthesized in laboratories built after Newcomb was dead and before Benford's paper was published, in the drainage areas of rivers on continents that neither man ever visited, in the half-lives of isotopes that were not discovered until decades after both men were buried. The law does not care about its own history. It does not care that it bears the wrong name. It does not care that the man who discovered it was a runaway apprentice, and the man who confirmed it was a flood survivor, and the man who proved it was a combat veteran, and the man who weaponized it was a South African accountant. It does not care that it has been used to convict embezzlers and flag stolen elections and audit the economic data of sovereign nations. It does not care that it was misused to fabricate conspiracy theories about a presidential election. It does not care about human institutions or human error or human justice. It just keeps working the way gravity keeps working, the way entropy keeps working, the way every fundamental pattern in nature keeps working, whether anyone understands it or not. And that, I think, is the part that should stay with you, not the forensic applications, as important as they are, not the election controversy, as instructive as it is, not the naming injustice, as real as it is. The part that should stay with you is the mystery itself. You are living in a universe that generates numbers according to a specific, non-random, logarithmic pattern. This pattern was discovered 145 years ago. It has been confirmed across hundreds of datasets and dozens of scientific domains. It has been proven mathematically necessary under conditions that the universe consistently meets. And the finest mathematicians alive have publicly stated in published, peer-reviewed papers that they cannot explain why. That is not a gap in the curriculum. That is not a fun fact for a cocktail party. That is a statement about the structure of reality itself. The universe has a preference. It prefers the digit 1. It prefers logarithmic spacing. It prefers multiplicative growth over additive growth. It prefers scale invariance over scale dependence. And nobody knows why. Nobody can derive it from anything deeper. Nobody can explain it without invoking the very pattern they are trying to explain. The circularity is not a failure of ingenuity. It is a feature of the problem. The pattern is so fundamental that there may be nothing underneath it. It may be bedrock. Every number you will encounter today carries the fingerprint of this pattern. The price of your coffee, the distance to your office, the balance in your bank account, the population of your city, the number of steps you will walk, the number of emails sitting in your inbox right now. All of them are drawn from distributions that obey Benford's law, and all of them carry the logarithmic bias toward the digit 1 that Newcomb noticed in the worn pages of a book in 1881. You were never told about this. It was published, verified, replicated, formalized, extended, applied, misapplied, debated, and confirmed across 145 years of continuous research. And it was quietly left out of every mathematics class you ever took. The most universal pattern in numerical data. A pattern that governs everything from the lengths of rivers to the half-lives of radioactive atoms to the daily behavior of global financial markets was never mentioned. Not because it is wrong, not because it is trivial, not because it is controversial, because nobody knows how to explain it, and the educational system does not teach things it cannot explain. But the pattern does not need to be taught to be true. It does not need to be understood to keep working. It does not need your permission or your comprehension or your belief. The numbers are not random. They never were. The universe generates them according to a specific logarithmic distribution that was first written down by a self-taught astronomer who ran away from an abusive apprenticeship in New Brunswick. Published in a 2-page paper in 1881, forgotten for 57 years, rediscovered by a flood survivor in a General Electric lab in Schenectady, confirmed across 20,229 observations in 20 datasets, proven mathematically necessary by a West Point combat veteran at Georgia Tech, turned into a forensic weapon by a South African accountant in Cincinnati used to convict embezzlers and flag the economic data of nations, misused to fabricate election conspiracy theories, and studied by the finest mathematicians of 3 centuries without producing a satisfactory explanation for why it is true. After 145 years of data and proofs and courtroom testimony and international conferences and tens of thousands of pages of published research, the people who understand it best have told us, in writing, that they cannot explain it. The data has been sitting there since 1881, in the worn pages of a book of logarithms that nobody thought to ask about. In the drainage areas of rivers and the populations of cities and the half-lives of atoms and the daily closing prices of stocks and the Fibonacci spiral at the center of a sunflower and the rotation frequencies of dead stars spinning in the dark. In every set of numbers that nature has ever produced and will ever produce. The pattern is there. It was always there, and the most honest thing anyone has ever said about it was written by a GE physicist in 1938, a man who survived a flood as a child and spent his life studying light, who looked at the data and concluded that it goes deeper among the roots of primal causes than our number system, unaided, can explain. He was right. It does, and we still cannot see the bottom.